Okay, so yeah, you guys can really just unmute yourselves unless there's too much background noise. Oh God. Okay. Um. All right. Let me get started with this talk. So I just wanted to talk a little bit about variational calculus, which is basically the language in which. Okay, let me start over because Mukund is saying he has issues, and there's only like two people, so might as well just wait for everyone. Mukund, are you there? Okay, yeah, I think he'll be here. I'll just go. Yeah,
Voice
okay.
clear, like
Yeah, it's clear, dude. He's much
okay,
better than last time.
yeah,
Oh,
okay.
okay, cool. Uh, Obviously, you guys must have seen this whole abstract and okay, you know what? I'll start. Okay, so I'm here to talk about variational calculus. So let me get started. Uh, Obviously, you guys have seen the abstract, and you guys must have seen the summary of the whole talk. Well, okay, obviously this summary is a little different from what I intended for the talk, and the reason is that there wasn't enough time to sort of fit in generalized eigenvalue problems. Maybe we'll look at it in a different day, when we're looking at linear algebra and so on. Let's get right on to this talk, and I've used these two books as resources for my talk. I would highly recommend that you check it out. This looks at variational calculus from a classical mechanics point of view, whereas the mathematical methods book looks at it from a very abstract view. And I've tried to combine both of these things. But again, I'm a physicist. I want to be a physicist, and my perspective is towards physics and classical systems. So that's where we'll be going. But there's also a lot of math that we'll be dealing with as we go through it. Right now, uh, let's get started. Why variational calculus? What's my motivation for this? Well, I'd say the key thing for me is I really just want to learn, Lagrangian and Hamiltonian mechanics and how and variational calculus is the language in which it is written. So that's why I care about, variational calculus. Nothing more than that, nothing less than that. And hi, Samat. Thank you for joining in. Right. So let me get started. So variational calculus is a special type of calculus. It's not too special. It's just a little different. It's just a little specialized. So what makes variational calculus unique, or what's the problem that we're trying to sort out? Variational calculus, right? So see, please give me a second. So let's say we have such an integral j with limits. Okay, so it needs to be the other way around, x1 to x2, or yeah, it's up to our preference. So, uh, well, we're integrating not a function. Just to note, we're integrating a functional, and it's a specifically constraint type of functional. And the constraint is okay. The first one is these two uh, variables are dependent variables, and they're dependent on x. All right. And obviously this is y and this is y dash, so it's just the dy by dx over here. And there's also another thing behind this. So visually you can look at this problem as trying to find the extrema, which is to say if I have such an integral, And I just want to find out a function f such that this j is a stationary point. Stationary point as in it should be a minima or a maxima. All right. So, well, we can then take this as okay. So we'll assume that there exists a stationary path where all along this path the line, every time you take a tangent, your derivative is just zero. So you could then express it as the path that you are taking as a perturbed path, which is to say that I have a weighting factor alpha times neta of x, where neta of x is basically going to describe all these points here. So it's my y of 0 plus this perturbation. All right. So the extreme path is the path where, dou j by dou alpha is basically 0. And your varied path is when you add the alpha times theta, right? So this isn't being streamed on YouTube, unfortunately, Amarjeet, but it will be on YouTube soon. Well, let me get back on track. So what is neta? So as I said earlier, it's just a function describing these points here. But also we have another important condition for neta. Two conditions actually. So neta must be continuously differentiable within these two limits, x within x1 and x2, and it must also vanish, uh, you know, to 0 at x1 and x2. So these are two assumptions that we're taking. And remember, we're only considering fixed points where x1 and x2 are there, right? So x1 and x2 are fixed, and neta is such that this is continuously differentiable, and it is 0 at x1 and x2. Now, let's try to discover what's going on in here, right? So I have this perturbation, and essentially, I just want this. This is what I want. This is the thing that I want to solve for. And once I get this, in physics speak, I will actually just end up with all my motions of equations of motion. And if I can solve those equations, I can basically predict to more or less a very certain degree as to how the object is moving, right? So we have this condition, and we have the two constraints that I mentioned for neta, which is it vanishes at x1 and x2, and it's continuously differentiable. And with this equation and with this condition that in mind, let's try to figure out what f might look like, or what might be within, right? So this equation that we'll discover is what is called the Euler-Lagrange. And let's get right down to it. So essentially, we just want to differentiate j by alpha, and you want to find out where its zeros are, right? Or where its stationary points are. So I can just take the differential operator, and I can take it inside the integral because the limits are fixed, right? And when I take it inside the integral, this is what I get. This is just calculus, right? Now, again, I'll just look at dou y by dou alpha and dou y dash by dou alpha, and this is nothing but we'll go back here. So dou y by dou alpha, it's pretty obvious that it's just neta of x, right? But dou y dash, y dash would just be y dash 0 comma x plus alpha times neta dash. So you would get these two equations, and we're just going to substitute them. And when we substitute them, voila, you get something like this. And it's pretty easy to see that you can integrate the second part of this in the right hand side by part. Sorry, there was a small connectivity issue. Can you guys hear me now?
Yeah.
All right, perfect. I'll just go on then. As I was saying, we can integrate this by parts, and that's what we will do. And if we integrate it by parts, we get this equation. And notice something. I have a neta here, all right? And my neta is 0 at x2 and x1. That's what we've assumed. It must vanish at x1 and x2. So this term will just become 0. I'll only end up with this, and I can just substitute this for this. It's going to put that back there, and I'll get this. Now, here's the catch, right? If I want my dou j by dou alpha to be stationary for any value of neta, right? That would mean that it doesn't depend essentially on the limits. It doesn't depend on my neta, but it depends on the things here. So these things must be equal to 0. And when you equate this to 0, you get what's called the Euler-Lagrange equation. Well, actually, it was Lagrange who discovered it, and Euler applied it to classical systems. So every time when you see it applied, it's the Euler equation or it's the Euler-Lagrange equation, and abstractly, it's just the Lagrange equation, right? Well, now we know exactly how the principle of minimizing the action works and what equation satisfies it, right? We'll look at a few special cases, and we'll look at a very interesting method that will help us with classical mechanics, and we'll look at two examples from classical mechanics. All right, so that's the plan in the next 30 minutes. Let's go for it. What happens if my degrees of freedom are not present explicitly? That is to say that in this function right here, if my degrees of freedom y is not present explicitly, if the equation f does not contain y but contains terms y dash and x, what happens? So we'll just retreat back here to the Euler-Lagrange equation. So if it does not contain y explicitly, when you differentiate it with respect to y, it will just be 0, right? So you've got 0 here, 0 minus dx by d by dx, and you have this term, and you can just integrate on both sides, and you'll just get this. So whenever you see a function that you're trying to minimize not having y explicitly, or the first a variable with not the differentiated variable but just the variable not being present explicitly, you must just think, okay, it's just dou f by dou y dash, and the RHS is a constant, and this is your equation of motion again in physics speak, right? But what happens if it doesn't contain x explicitly? So this is a rather roundabout thing. So I'm just going to go back here to the Euler-Lagrange again, and I'm going to multiply both sides by y dash, actually. And when I multiply both sides by y dash, and if I just do this, I'm just going to expand this out. And if I did expand it out, I will get something like that. And again, this is rather nasty. So let me just try to group things. And when I do group things up, right, what I find is that, so let's just look at the structure in the LHS. So I've got this and this, right? So if I have a function of f, and if I differentiate it, just to say d of f, df, I would get something like f dash, and then I would also differentiate the x term inside. So doesn't it look something like that over here? So we'll essentially, in such a sense, we would just group these two terms to find out that this is nothing but this is nothing but the derivative of f with respect to x, and x is not present explicitly, mind you. So that's why you have this really weird expansion present here. So you have df by dx is equal to dx d by dx of this thing. You can just integrate on both sides, and you'll end up with f is equal to y dash dou f by dou y, and you bring it to the other side, it's just you'll just get a constant, right? So this is essentially the equation that's going to help us whenever we find that x is not present explicitly. And it does happen sometimes in classical mechanics itself. You don't need to go to the other realms of physics, mind you. However, these are just us playing around with the parameters, there are more general variations that we can quite quickly get through. So let me get through a few of them. What happens if there are several dependent variables? Dependent variables are basically the y's that I have because they're dependent on x, right? And if there are several dependent variables, I will have, n y's. So my I is just a counting term from 1 to n. And similarly, I will have n number of equations for my perturbations or the parameterization of the line. And thus, I will have to sort of sum over the number of Euler Lagrange equations. So if I have n number of you know dependent variables, and I will certainly have n number of Euler Lagrange equations, right? But what happens then if I have several independent variables? What happens if I have n independent variables? If I have n independent variables, it's very easy to see that I must have n integrals because I am integrating with respect to the independent. So I will have n independent. I'm sorry, n. That's the number of multiple integrals that I'll have. And again, there's a small catch here. It's pretty similar to what we had here, except for the fact that there is a very weird yxi term. So yxi, just usually what we'll have here in the normal Euler Lagrange equation is you'll have dou f by dou y dash, right? But yxi is basically something similar to this. It's basically telling me dou y by dou. I'm sorry, this would be dou y by dou x, y dash, and this would be dou y by dou xi, which is, again, this is a bit of Einstein notation here. Dou xi basically refers to my sum. All right, but we're summing, we take the sum outside. So we're sort of multiplying, we're sort of doing this operation on it and then sort of summing it, right? So
Shouldn't it be like y dash of xi or something?
I'm sorry,
Is it just y of xi or like y dash of xi?
this is the weird y of xi is basically like I said, dou y by dou xi. So usually I only had one x beforehand, right, Mukund? Now I have like n x's. So that's why I have to, not only do I have to do dou y by dou x1, I also have to do dou y by dou x2, x3, x4. So that's what's happening here. Do you get me?
Okay.
Yeah.
Mm.
So that's why I have this sort of a weird, like, that's what y dash means, right? Y dash basically meant dou y by dou x. But the trouble here is I don't have just a singular x. I have n of them. So that's why I'm using this I notation here. And that's why it's a bit, it's probably something that we haven't come across yet. So yeah. Well, another interesting thing that we haven't probably tried right now is all of these are first derivatives. All of these are just first derivatives. So what will happen if I include higher order derivatives? Again, not going to go into too much detail because most of the time we tend to avoid higher order terms. But this is it's still worth study sometimes. So you will just get the dou f by dou y, but your other term gets an interesting generalization like this. And for instance, if you have some other contributions coming from the higher order terms, it will pop up in the RHS, but it'll pop up here. But we sort of do lose assurance as to whether or not these equations will be linear. So that's a bit of trouble that we run into, because every single thing that we've talked about, even these really wonky n number of variable cases, they're all n number of linear equations, and the numerical methods to solve them are fairly simple, and you just need to just copy paste a few of them into Mathematica, and it would just pump out an answer, or Python, and you just get your results. Only thing, you'd have to solve for n variables, but here not only would you have to solve for n variables, but like sometimes you would just have sort of lose your predictive power as well because of the non-linearity of the equations. But again, you can have higher order derivative terms in your F without having any contributions in the RHS. And this is perhaps this is what I was just telling you guys earlier, which is to say that this is the important thing for classical mechanics. You may have heard of this as constraining, Euler-Lagrange equations, or you may have heard of this as the Lagrange multiplier method, and so on. So we'll get right to it. Okay, so the question that this setup or this whole concept is asking us is, okay, I have my Euler-Lagrange equation. I just want to minimize this J. It's all the same thing, same, same starting and end points, fixed points. My neta is continuous within that interval when it vanishes at the end points. All good. But let's say I have multiple variables, which is not multiple dependent variables to be precise, which is not too much of a stretch because we're just going to have to sum them like this, right? But here's the thing: what if I have a constraint? So, well, what is a constraint? Well, if I have a system, let's say a rotating rod, then you could say that a constraint or a limitation that you're placing on the system, apart from the fact of really just saying no air resistance or something of that kind, that's more of an ideal condition for solvability. But a constraint that you would set on it would be to say that it would only rotate in a circle because, and this radius of the circle is going to remain unchanged. Or if I have a rolling ball, this is a very classical problem down a slope. This is the only direction it's going to take. Gravity is always acting downward. So these are constraints that we can place on our equations, and we'll see why this is powerful, or why this particular method is powerful. So I'm gonna describe my constraints by the letter G here, and my constraints, I'm constraining Y and Z, which are dependent on X, right? So what do I do? First thing, I just want to differentiate it, and the constraint I'm placing is such that it's 0. All right. So a second. All right. So if I differentiate it with respect to alpha, this is precisely what I'll get. Just normal calculus. So let's keep this in our head. All right. Let's keep this. And also, I'll have I'm involving 3 variables, which means I'm sort of in 3 dimensions, and the way I can perturb my my path of my stationary path can be this way, or I can put up it in this direction completely. So I have like 2 degrees of freedom here. So what I'm going to do is this is basically my way of saying, okay, my perturbation in Y can be described as this, my perturbation in Z can be described, all right? So now what I'm going to do is I'm just going to differentiate this because I've got this, I want this term and I want this term, let's say. So I just got to differentiate Y with respect to alpha, I'll get neta 1. And if I differentiate Z with respect to alpha, I'll get neta 2. And that's what I'm doing here basically. I'm just going to substitute this here. And if I sort of mix match stuff up, I'll get this equation. And if I mix match this equation, I'll get this. All right. So I can just substitute this back into the giant one that I had, which is the equation that we're trying to trying to extrematize or make it stationary, right? Right. So now I'm gonna take this and put this in, and I want to take neta 1 out. Okay, I'll tell you guys why I'm doing this. So I'm just gonna take neta 1 out, and I can do this by this sort of substitution. I've taken neta 1 out. Well, this looks almost exactly like our original Euler-Lagrange equation because I've got 1 neta 1 out, and then there are all these wonky terms inside. So, just using the same logic that we used earlier, we'll just go with saying that for any arbitrary theta 1 of x, or any arbitrary, fixed points, my j has to be stationary. That's the problem that we're looking at. And that means this entire thing is zero. Only if this is zero can we arbitrarily sort of switch between them. So I'm just going to equate this to zero, and I'll get this by rearranging it. And here's the thing. If you notice it, so it's a rather weird equation, and it's almost very almost perfectly arranged. Uh, and I'll tell you why. Because there is no function that's dependent on x. I mean, these are implicitly dependent on x, all of these things, but there's no clear explicit mention of x. So technically speaking, you can sort of bring in, I'm just going to arbitrarily put it as minus lambda. And the reason I'm putting it as minus, it can be plus lambda as well. The reason I'm putting it as minus lambda is because I really just want to bring it in. So if I have this minus lambda such that I can sort of rearrange it into two equations. And this minus lambda has a special name. It's called the Lagrange multiplier. And again, once again, it's called Lagrange because he basically did a lot for us physicists, right? And well, this is basically describing my constraint in a sense, and I'll get to that in a minute. All right, so if I can sort of rearrange, I'll get these two equations, and I can generalize these using this equation. Well, there does seem to be a bit of an absurdity here, if you ask me, because I've got, this is an unknown, this is a random thing that I just dropped in on your head, and I don't know what's going on here, and I don't know what's going on here. So I've got three equations. I'm sorry, I've got two equations right now in my hand, but I've got three unknowns. Technically not solvable. But that would only mean that we have forgotten something. And what have we forgotten? Well, simply put, we forgot that the equation G, exists. So this is a very interesting thing. So I've limited my sort of set up my system, and this would just give me my third equation, and I've got three equations, I've got three variables, and that means it is solvable. And mind you, again, these are linear equations, right? So this is basically a way of writing what is called a Lagrange multiplier. Again, this will be undetermined unless you solve this equation. But why is this method powerful? Why is it used in classical mechanics? There are two ways to do this, and one is just right in front of your eyes, which is to say that if I can, this lambda j is a weird thing because that means I can arbitrarily introduce more and more constraints, n number of constraints, and all I would need to do is just add them, and my equation would still remain linear. Okay, so that's one very powerful tool in our toolbox. That's one reason why it's so powerful. And another reason is obviously you can use different kinds of multipliers depending on the problem. You can sort of arrange, choose, or constrain things appropriately to make sure that you don't necessarily need to get the same equation of motion for the same system, but you can get what is called equivalent. And this is yet again a neater way of writing it. Well, in a very loose sense, you're basically counting to m here, and you're counting to n for I. So in a very loose sense, you will have n plus m equations, where is the contribution of the m number of constraints, and n is the contribution of the n number of dependent variables, right? So you technically have n plus m equations. Here, in a sense, you can quite loosely say I only have n equations to solve, right? So I'm just going to pause here because I felt like I did go through it intensely. So any questions or anything you guys can raise it now. Before we go to because the next slide is just notation, and after that we'll jump right into two examples in classical mechanics. Any questions?
Completely lost.
I'm sorry.
I'm completely lost.
I'm sorry. Okay, where do you want me to start again
Yeah.
from?
No.
I can't hear you, Amajit.
Need to talk.
Mukund, can you hear Amarjit clearly? Because I can't. Amarjit?
Yeah, I think I'm having some network issues.
Okay, but can you type your question out?
Yeah, I'll type mine. But
Mukund, what about you?
Yeah.
Questions? Or did you get it?
Yeah, it was understandable. I mean, I had a little doubt basically in
Mm-hmm.
that
But
the above part where you explained the constraints thing. So I just wanted to get more, clarity in that.
yeah, go on. Which part
Yeah,
exactly?
where you explained the constraint G.
Hmm. This part. You mean
Like
this part.
we already constrained it, right, in the previous one, like assuming that equation to be zero.
Yeah, this is the constraint.
And yeah, so like why do no? This is one. Then for the above one, right? Like we calculated one constraint, that equation to be Euler-Lagrangian equation to be zero, right?
That's not a uh, that's not a constraint technically speaking. That's more of a
Assumption, no
it's a condition because
condition. Okay.
uh, the problem is asking us what will make
Hmm.
this zero. That's not a constraint. That's not us
Okay.
limiting the system.
So
That's the
okay.
problem itself. So it's a little different, a very subtle difference.
Okay. Yeah, that's why I was like, why do you need like two constraints basically in this when you already have? That's why I added out as it.
Okay, maybe Amarjit, what I'll do is uh, I'll probably uh, just rush through the examples. Yeah, that's what I was exactly thinking. So I'll do the examples and we'll come back to the theory again. All right. This is more of a okay. The slide that you're seeing right now is more of a notation that is used, and it just sort of again delta here again. Hello. So it's more of a very neater way of just writing things, right? And the way it works is just given here pretty much, and you can then rewrite the condition of extremum to say that okay, a small perturbation, a small perturbation should just be, or say that despite the small perturbation, my path of my stationary path is somewhere else. And it can be visualized as such, and this would just be your delta of, whatever it is, or delta of y, sorry. And this is called virtual displacement. And it's called virtual because technically we're not in physical space, despite what the x and y axes are showing you. There's also a y dash, right? So you're in what is called configuration space, and configuration space usually you have three variables for a particular thing. So you have y dash, and x, where y and y dash are dependent functions of x, right? This is more of a sanity check to see if this notation really helps us. So if you take the delta j and if you take the delta inside, you can sort of expand it likewise. And well, this makes sense, but what does delta y dash mean? Delta y dash basically means delta of dy by dx, and I can take the dx outside, I can just let the delta stay in, right? But here's the catch. Again, I can sort of integrate this by parts again, and well, you know what happens. So the first term disappears due to neta being there, and the second term exists, and we just bring back the second term, and this is just a version of writing the Euler-Lagrange equation, right? And we'll get to examples now. Since we're armed with this barrage of knowledge, or this understanding, or this instinct of what this form of calculus is, we'll go into two problems. We'll do one in which is called the Fermat's principle in optics, and two, the second problem would be a vibrating string problem in Lagrange mechanics, and it's called Hamilton's principle when it's applied there, or D'Alembert's principle. So there are just a lot of different names given to the same principle, which is just to say that I want to minimize my function j. This is all that we're looking at. So the thing in Fermat says when it comes to optics is if I have a ray of light that is passing between two different media, where okay, so for us we've had a system here, and the system is such that n2 is greater than n1, right? N2 greater than n1, and my ray of light sort of moves this way. And what Fermat says is actually, if I take the actual path traveled or traversed, and if I call that L, and if I have a the refractive index n, if I multiply those two, my the light ray moves in such a way that it minimizes uh, this product. Again, this is pretty non-standard notation, so don't take it pretty much at face value. I'd rather have you guys think about the concept. So it's just that I'm trying to minimize the product of the length of the path traveled times the refractive index, right? Before we go any further, I will just sort of drop in a different angle. So this would be phi 2, right? So and this would be phi 1, or wait a second. Yeah, sorry, this would be phi 2. This would be phi 1.
Okay, what is alpha here?
Alpha is just the when you are having the curve, you would parameterize it by a parameter alpha.
The line, the curve following the path of alpha will be the least with the minima, right?
Yeah, where alpha is 0. So like if we go back to the very first set of slides, you'll see that I've basically parameterized this curve by a variable alpha, and the condition is that when alpha is 0, you will get the extremum path. Clear, Amanjeet?
Okay, so I'm now confused. What do you mean by parameterizing?
So yeah, right. So what I'm doing is I'm breaking down this curve. Okay, this can be any curve between these 2 points, x1 and x2, all right? But I am trying to say that there exists a curve, okay? There exists a curve, this curve to be very specific, such that, yeah, so such that my entire j, is a stationary point. When I differentiate j by something, or my parameter here, it is basically stationary. All right, so this is the curve that we're looking for. This is the curve that we're in. All right, so the curve that we're looking for is called the extremum path, and the curve that we're in is called the varied path, and this is called virtual displacement. The displacement between the curve, the extremum path and the varied path, and this is called the virtual displacement. Now, what happens here is that we're again the basic statement of the problem is I just want to find out what happens. What is the function y that makes this a excuse me, Uh, Apologies for that. Yeah. So you just want to make y a stationary point. That's the problem. So the reason we break y up like this is to say that, okay, I will find this extremum path when say, this is all the language in which that's written, right? So
Okay, I get it now.
so we were just looking at Fermat's principle, and his is such that I want to this product of the total path traveled times the diffractive index of the path in which it is traveled should be stationary. That's the idea for Fermat's principle, right? And that can be expressed mathematically like this, which is to say, I
And
have to
once again, like in the previous diagram, the graph, so like
this is
shouldn't
not a graph.
N1 be greater than N2?
Um,
Because like you see, like
okay, that's really not. Uh,
no,
it really
like
doesn't
this is
matter, but yeah,
okay.
I give you that. Yeah, you're right. But
No,
that's
like then your function, your okay, no.
no. I'll tell
So
you why
that
it
doesn't
doesn't matter.
affect my NL, right?
Yeah, it doesn't matter. I'll tell you why. I'll tell you why. Just wait for a second. So these are my. I'll consider like we've applied this method generally. Now we're going to apply it to a very specific problem. Watch closely. So these are my fixed points x1 and x2. So I'm just going to call them a and b now, and
Okay,
they
so
will
like we
form my.
assume that the function will be result to zero at those points.
Yeah, it will
Mm-hmm.
result to zero at those points.
Mm.
This
Okay,
yeah,
okay. Yeah, then it
this
won't matter. Okay,
function.
okay.
Yeah, then it really doesn't matter.
Yeah, yeah, yeah.
No, because think about it. If my light ray is traveling from A to B,
Mm.
right, and this is basically the length traveled, and
Mm.
what is it? And you can arbitrarily consider this to be a starting point or this to be the starting point because
Mm.
of a reference framework,
Mm.
and yeah, so it really doesn't matter. But what I'm trying to drive at here is let's just take a look at this mathematically using what we've just sort of seen, right? So this is my refractive index, which is dependent on where I am. All right, guys, can you hear me?
Yeah, yeah, yeah.
Yeah. So, and this is my length. It's basically the formula for length, and I'm
Okay.
just
Oh,
gonna
once
write it
plus
out,
plus. Okay.
and dy by dx the whole square root divided by 1. It's a very terrible way of writing it, but yeah, so essentially what it is. Now, here's the thing: as we've seen earlier, if I want to really just if this is just going to be, this will just be uh, uh, if I want this to be stationary, if I want this entire thing to be stationary, then it's going to
Mm.
just be equal to 0 or a constant, right? So
Okay. Mm.
let me do some very basic trig here. That's all. So dy by dx is basically tan theta, right? And this is dy by dx the whole square. So I get 1 plus tan squared theta. I'm sorry, tan squared phi. I'll take phi here. All right. So what happens is 1 plus tan squared phi is basically secant squared. Secant squared phi, and inside the square root, it becomes secant phi, and I take 1 by secant. I'll just get cos. So that's how I end up from here to here. All right.
Wait, we need p to be 0, right?
Yeah, you want p to be minimized.
Minimized. Yeah, so it should be 0, right?
Yep.
Basically, like.
Yep.
So then
The
my
differentiate when you differentiate.
yeah. So
So
my
so what I'll do is if I just differentiate it, okay, and it's 0,
okay.
and if I integrate it on both sides, I'll just get
You need
a
dp by
constant on the right.
dx to
I'll
be
just get a
0. Okay.
constant. Yeah.
Mm.
So again, this can be rewritten as n sine theta because of how I've arranged my angles, and yeah. So these are
Okay,
just
so
complementary
this
angles of each other. So, and I'll just end up with this. This is something that we've seen
Snell's
literally
law.
all our
Yeah.
life. Yeah, exactly. So, and this is pretty much describes the motion of your light ray through two different media of two different refractive indices. So yeah, you can see how we just used one principle, a little bit of math, and you ended up with the equations of motion. So yeah.
Okay, cos
And
phi sin theta. So okay,
yep. Another sort of example is in Lagrangian mechanics, which is what Amarjit was sort of talking about earlier. So in Lagrangian mechanics, this f turns into a function that's called L, which Chinmaya must have hinted to. The cos phi turned to sine theta because they were complementary angles. So phi is equal to 90 minus
90
theta.
minus theta.
Yeah.
Or you could say opposite angles.
Oh yeah, opposite angles. Yep. Well, what we're doing in Lagrangian mechanics is we're trying to minimize this integral, right? And this is conveniently called the action. Okay, and this isn't standard. I don't know why the books used it, so I went with it. But usually you denote it as a, and you would say my delta a should be 0 or stationary, right? So stationary action. So principle of stationary action is probably the right way to say it. Least action, you don't need to say least action because you can also have it as an extrema, right? As we've seen, you just want the first derivative to be 0, right? And L is actually defined very particularly as T minus V, which is to say that it's the kinetic energy minus the potential energy of the system. So we'll look at a toy model and see how we arrive at the equation of motion. And this is an equation that we all are very familiar. So let me take a string vibrating in a single dimension. All right. So obviously the string's got a length L, and I'm also going to throw in two more parameters for the string, which is I'm going to throw in two local parameters, rho and tau. Yeah. My tau will be my local tension at any given differential dx, and my rho will be my local density of the string. All right. So again, this is a constraint that we're placing on the string 0 to L. That's my maximum length, and we're not placing any constraint as to how how high it's going to vibrate or those
Density
kinds
of
of
the
things.
string.
Density of the material of the string, yeah, rho.
Okay.
This is local density. So it's if I take a small segment dx. So these are basically functions of x. Just keep that in mind. When I say rho and tau, I basically mean they are functions of x and they're very local to this thing. They aren't constant everywhere, right? So now I'm just going to rewrite my Lagrangian. So my Lagrangian is T minus V, but I can actually write it in terms of my density and tension. All right. So that's essentially what I'm going to do, and this is how we can sort of rewrite them. All right. And I'm not going to give you an explanation yet as to why we write it because I am a little confused with that as well, to be honest. We'll get there. But let's first sort of apply this. All right. So T minus V, I'm just going to subtract this minus this. All right, and I'll end up with a integral again here. Well, if this is minimized, then this entire thing is 0. I do a little bit of rearranging, you know, I'll just get, uh, I'll get tau by rho times y double dot, and I can just rewrite tau by rho as 1 by c squared. Dimensionally, these two are correct if you consider c to be the velocity. And we just used one principle, and we arrived at the equation of the vibration of the string far more smoothly, which is to say how uh, useful, if you think from first principles, can be. And also, it's a demonstration of the power that variational calculus gives you, and what Lagrangian mechanics can give you as well. I hope, Mukund, you remember when we were in class trying to derive this tiny equation.
Mm.
Yeah, yeah.
Uh,
So this just got over. Everything just got over. So yeah, uh, with this,
just
I would.
thinking how we got that potential
Mhm.
to be to that form. Yeah,
Yeah, I'll get there. Give me a second. So, where is that example from?
it's like for the
And again,
kinetic
yeah.
energy is like it's understandable. Like you have half mv square and then this thing, and then like potential. I don't know.
Also, yeah. Well, one assumption that we've continuously made is that we've assumed that our points are very just going to uh, be stationary. X1 and X2 are stationary. They needn't be stationary is also something that you guys should know. You should be able to move one of those points, but in a predictable way, and still preserve this principle of stationary action. Which is to say that I can have my point x1, and I can say that my point x2 moves in a straight line or in a circle, and then sort of apply the same principles yet again. All right, and if you'll observe this equation, this is an equation of motion, but you can also arrive at this equation by taking uh, by just doing this to the Lagrangian, not to the fancy L, but just to the L, d by dt times dou dou L by dou q dot. So you guys can just try
Oh
it,
yeah,
and
yeah, yeah,
you will just
yeah. Mm.
I'm sorry, yeah, you will just end up with this equation
Mm.
right here. Uh, yeah. So why do we get that? Why is the kinetic? I mean, it all fits. It all fits perfectly. But why do we get that formula for kinetic and potential energy?
Which
These two equations. So first thing would be to have a dimensionality check. So this is a function of y of t. So that would mean this would be
it's like v
um,
square
this
type
would be
thing.
mt inverse dimensionally. This would be mt inverse squared. So you'd have m squared. I mean, I think it'll dimensionally tally up. I mean, like equations are basically forward backward, right? But you should also have a dimensional tally. So this is m squared t minus. So rho is basically uh, kg meter inverse. I mean meter cubed, right? So just get a,
Yeah, rho dx is like the mass, and
Yeah, yeah.
then
Mass same this thing. Yeah.
then
Mhm.
del
Uh,
y by del t is
mhm,
Then your dy by dt could be like your velocity square. Then
mhm.
velocity, and then rho dx is the mass.
mass
So your rho by 2 dx, this whole
half
integral would
mv
just be,
square.
yeah, this is just half mv
Yeah, yeah.
squared.
But then like for the mgh, that's what I was thinking. Half. How do you like?
No, your potential needn't be mgh all the time, right? So, but let's see.
What is tau?
How's
Now
this thing tension? No, local tension.
local tension.
So tension is
Tension is the same units as pressure, right? Kg
by
meter second squared per meter by meter squared, which is
Force.
okay. So yeah, well, let's get to this.